So now that we have been introduced to the idea of a one register stack machine and how one could potentially do code generation for such a stack machine. For example, we looked at the language of expressions. Let's try to look at a more featured language to discuss our code generation strategy. Unlike our previous language, which is just the language of expressions involving constants, in this particular language, we have a grammar. The grammar is shown in this slide. The top level the non-terminals are P, D, args, and E. So let's start with E. E is the non-terminal that represents the language of expressions, and it could be an integer, which is the constant integer 1, 2, 3, 4, 5, and so on. A variable ID, identifier, or expressions formed by recursive constructors like if then else. So if E equals E, then E else E, or E plus E to represent addition, E minus E to represent subtraction, and a function call, an identifier, which is the function name applied to a comma separated list of expressions E, comma E, comma E. I've just labeled them as E1, E2, E, but they're just E's here as well. So that's the language of expressions. So for example, 2 plus 3 is an expression, x plus 2 is an expression, f3 is an expression, fx comma 9 is an expression. If x equals y, then 2 else 3 is also an expression, right? So these are just examples of expressions. Now, the other non-terminal here is args, and D and P. So D basically represents declarations. Okay, so D represents a single declaration and a declaration of a function or a definition of a function. And it requires a def keyword followed by an ID, which is ID represents a variable identifier. In this case, it's a function identifier. And open parentheses, close parentheses, and args. So args is the formal arguments, the names of the formal arguments of the function that we are going to define, equals E. So the idea is that the function f takes as inputs these formal arguments args, as represented by args, and then makes a computation as denoted by E. All right, so that's what it means, and then somebody can call this function to evaluate E for the arguments supplied. We're going to see that as well. And what is args? Args is a non-terminal that is just a comma separated list of variable IDs. All right, so args is not expressions, notice. Args is just variable IDs because these represent the formal arguments, not the actual arguments of the function. And then finally, the top level non-terminal P represents a semicolon separated sequence of declarations, function declarations. So P is either D semicolon P or D. All right. So notice that the program should have at least one declaration. Also, the idea is that the first function, the first declaration is the entry point. All right. So we assume that the first function is the entry point, and from there the computation will start. So let's look at an example to understand this language a little bit better. Here's an example of a function fib. Fib takes a single argument x, and this is the expression that it computes. It says if x equals 1, then 0, else. If x equals 2, then 1, else. Fib x minus 1 plus fib x minus 2. So notice that this whole thing is an expression. This is a variable ID, or also can be produced using the non-terminal args. And this whole thing here is a declaration, and also it's a program. All right, so anyway, so this particular program, as you can imagine, computes the xth Fibonacci number, because this is just exactly the same logic that you would use to compute the Fibonacci series. And notice that a function call here, fibx minus 1, is a recursive function call. It doesn't matter if recursion is allowed in our language, and in this particular case, this is also an expression in our grammar. All right, all these are actually expressions. All right, so this is an example program, and we want to understand how one would generate code for such a program for our one register stack machine. All right, so what we are discussing now, so we already discussed a simple language of expressions. Now we want to discuss code generation for a more featured language that has function calls, if then else constructs, and function declarations. All right, so once again we are going to follow the same invariant that we had when we were discussing code generation for the language of expressions. For each expression E, we'll generate MIPS code that computes E's value in the accumulator A0 and preserves the stack pointer and the contents of the stack. So this is exactly the same invariant that we're using when we were discussing code generation for the language of expressions. So we're going to define a function cgen such that cgen takes as input an expression E. For example, it could take an expression if then else something. So it could, for example, take the entire body of the function fib as an argument, and its result is the code generated for the expression E. Now I'm going to define this. So our job to, our code generation strategy is going to be defined by this cgen function, and we are going to define cgen based on recursively, inductively, based on the operators that are supported in our language. So for example, cgen for I, which is where I is I is the representative for an integer. So cgen for any integer I, a constant integer I, is just load immediate I into A0, right? Because that's going to follow our invariance, which is the result should be in A0 and the stack should be clobbered. All right, let's look at another example. So let's see, I have cgen of E1 plus E2. So notice that when I'm specifying cgen in this way, I'm basically using E1 plus E2 as a template. So E1 can match any expression and E2 can also match any expression. So basically I'm just structurally defining cgen over the different operators that can form the structure of an expression. So cgen E1 plus E2, I need to first generate the code for E1, then save the result, then generate the code for E2, and then do the addition, right? And so that's exactly what we're going to do. This is something that we have also seen when we are generating code for expressions. So I do cgen E1, then at this point here, I expect the result to be in A0, right? And so what I do is I save A0. So this is just a strategy of code generation, right? So I save A0 to the top of the stack. Where's the top of the stack? It's at $0 $sp. So at exactly where $sp is pointing, the stack pointer is pointing. And then I also decrement the stack pointer to show that the stack size has increased. So I use add IU, which is add immediate and update, $sp minus 4. Then once I have saved it, I can now generate code for E2. Now, because of our invariant, we can be sure that cgen E2 is not going to clobber the existing contents of the stack. And it's also not going to change the stack pointer. So it can potentially push within the cgen body, but by the time it returns, it would have popped the stack, so that stack remains exactly as it was before. And at this point, the result is in A0. A0 has the result for E2. And top of the stack has the result for E1, because that's what we pushed and we assume that it hasn't been modified. So what do? I load the top of the stack, which is $sp, into the temporary register T1, and then I do addition. I say add A0, A0, T1, which is just going to put A0 plus T1 in A0. And so now the result of E1 plus E2 is in A0. This is exactly what we wanted, but we can't stop here. We can't finish here, because in this whole code generation strategy, we have also modified the stack, because we have incremented the stack pointer. And so I want to, I want to kind of, so we had decremented the stack pointer. So we had increased the size of the stack. Now we want to pop back. So this was a typo. It should be +4. And so we want to basically release space from the stack, so that if there was somebody else who's using this, who's calling this recursively, he can see the same stack as he entered. So the stack state at the exit of this strategy, of this implementation, is the same as the stack state as the input. The only difference is that A0 now holds the computation result of E1 plus E2. Alright. Now, I want to point out that I'm using color coding to denote the different parts of my code generation function implementation. I'm using red to represent all the static parts, so the calls that are being made at static compile time. I'm using E1 plus E2 as, so I'm using these blue font for representing the expression syntax, the higher level program syntax that has basically being used as, being used as arguments for the cgen function. And I'm using the green font for the instructions that are actually getting generated that will be executed at runtime. And so the right way to write this implementation would have been to put print statements that would, that would be executed at compile time. So, print would get executed at compile, this print would execute at compile, and the next print would execute at compile time. But just to remove the extra syntax, I'm just using this particular representation where I'm just getting rid of all the prints and just using color coding to say that this is what's going to get printed in the output stream. The whole operation is happening at compile time, just that these green things are going to get executed at runtime, and right now we're just printing them out to the output stream of the executable. Okay, now here's a question. Why do I need to store A0 at the top of the stack, and why do I need to push A0 to the stack? Why could I and then later load from the top of the stack into T1? Couldn't I optimize and just put A0 into T1 using the move instruction? So the answer is actually, it looks very inviting to do this because it's an optimization, and it seems like T1 is, all I'm doing is pushing and then popping into T1. Why not I just move into T1 directly? But it's going to be a mistake because there is no guarantee that cgen E2 will not clobber T1. All right, and if cgen T2 clobbers T1, then the code generation strategy would be faulty, and so that would, because that's not part of our invariance. So here is an example. Let's say E2 was equals E3 plus E4, then surely T1 would have gotten clobbered during cgen E2, and so this would have not worked. On the other hand, if we push it to the stack because of an invariance, it would have still worked. Alright, so this is our code generation strategy for E1 plus E2 operator. We can similarly generalize this for other mathematical operators. For example, if instead of plus I may have minus, and so if I have minus, the only change that happens is in this particular opcode, instead of add I have subtract. Okay, now let's look at another interesting example which is different from the typical operators plus, minus, multiplication, etc. This is a branching operation. If E1 equals E2, then E3, else E4. What would be our code generation strategy for a construct like if then else? Now, to be able to talk about this, I need to introduce two more relevant opcodes from the MIPS architecture. The first opcode is branch if equals, that takes two registers R1 and R2 and a label, and branches to label if and only if R1 equals R2. If R1 is not equal to R2, it behaves as a no-op, which means it just moves to the next instruction. If R1 equals R2, then it just changes the PC value, next PC value, to whatever is specified using label. So this is a conditional branch, conditioned on the equality of the two operands R1 and R2. There is another operation which is an unconditional branch. It's a branch label. It just unconditionally branches to label. So if I wanted to generate code for if E1 equals E2, then E3, else E4, what do I need to do? Well, the first thing I need to do is I need to evaluate this particular expression E1 equals E2, right? And only after I get the result will I be able to make a decision whether to go to E3 or E4. So I first generate the code for E1. So I say cgen E1. And then once again, the next thing I want to do is perhaps cgen E2. But before I can do that, I want to save the result of E1 because I don't want it to get clobbered. So I just push it on the stack using these two instructions. And then I do cgen E2. All right. And at this point, I'm ready at this particular point after cgen E2, I'm ready to compute the equality relation. And to compute the equality relation, I first load from the top of the stack into T1, just like we were doing for addition. And I'm going to use the branch equal to check whether they are equal or not, and depending on that I'm going to either jump to a label called true branch, or I'm going to fall through to the label false branch. Okay, and both true branch and false branch are going to do some computation. Typically false branch would just compute E3, false branch would compute E4 and true branch would compute E3, and then both of them would branch to the end of this whole expression computation, which is end if. Okay, there's one more important thing you need to be careful about, which is the second invariant. So notice that whatever is computed by false branch would be in A0, and so by the time we get to, irrespective of which branch we go to, the result would be appearing in A0, because both E3 and E4, the code gen for E3 and E4, we can assume that the result would be generated in A0. But what about the stack pointer or the stack? Notice that to compute E1 equals E2, we had modified the stack, but now we don't want to, we want to release that particular space. So either I could have released this space in the indif position, which would have been also fine, but it's better to release the space as soon as possible so that you can save space. And so in this case, I just do add IU $sp $sp4 immediately after the load word, because at this point I don't need, the top of the stack is dead, and so I can release space. So release the space. All right. Now, so this is the code generation strategy for if E1 equals E2, then E3 else E4. You first generate code for E1, then you save code for E1, save the result for E1, then you generate the code for E2, then you do the computation of equality. No, you don't do the computation for equality, that's in BEQ, but you restore the stack to the state that it was. So you pop off the stuff that you had saved for storing the result of E1, and then you execute this branch equal to instruction that's going to check. So yeah, one of the things you do is you load the result of E1 into T1, and then you check whether T1 and A0 are equal. If they are equal, then you jump to the true branch, otherwise you fall through to the false branch. Inside the false branch, I'm going to execute, I'm going to generate the code generated by cgen of E4. Inside the true branch, I'm going to generate code generated by cgen of E3. So whatever is the code that is required to compute E4 will appear here, and whatever is the code that is required to compute E3 will appear here. Okay. This is the complete picture in a single slide. Cgen of E1, if E1 is equals E2, then E3 else E4 involves first cgen E1, save the result of E1 by pushing it to stack, then generate the code for E2, load the saved result of E1 into T1, release the space in the stack by popping off the top word, check whether T1 is equal to the result of E2, which is in A0, and if it is, go to true branch, otherwise go to false branch. At true branch, generate the code using cgen of E3. At false branch, generate the code using cgen of E4. In both cases, after you've generated the code for computing the respective expressions, branch to end if, and that's the end of my implementation for the if then else construct.